Alright, so I'm Stephen Giancarlo and I'm presenting on the Fourier Series. And first we'll start off with some quotes. We get to record my butchering of French for posterity. L'étude profonde de la nature est la source la plus féconde de découverte mathématique by Jean-Baptiste Joseph Fourier, which is roughly the deep study of nature is the most fertile source of discoveries of mathematics. And also, if you want to find the secrets of the universe, think in terms of energy, frequency, and vibration by Nikola Tesla, which translates to if you want to find the secrets of the universe, think in terms of energy, frequency, and vibration. Seems halfway relevant to the Fourier series. So, one of the first important concepts of the Fourier series is the usage of analysis and synthesis when working with waves. After all, Fourier series is about finding the components of a complex wave or wave-like function with simpler sinusoidal functions. This is accomplished by analysis. Now, you may also want to combine multiple simple waves into one complicated or but less data-intensive wave for things such as data compression with audio files. Both of these are accomplished with linear operators such as integrals or series. Now, linear operator, if you're wondering, is able to retain, I believe it's scalar multiplication and also addition of two values in its vector field. I won't get too much into that. Another important concept is periodicity in time and space, as these are both variables that may come up with the Fourier analysis. As you may know, periodicity is a repetition of a pattern. What you may not know is that this pattern does not have to be just in time. Time, or so I put here, temporal periodicity, is probably the most common form you encounter with, say, frequency. After all, I did mention waves, and they do have frequencies as one of their most important components. However, there could also be spatial periodicity. Just think in terms of, say, tessellations, or if I had a rectangle that's divided into equal sections, then these sections occur in a repetition and a distinct pattern. And both of these can come together in the form of traveling waves, where you have the wave itself is moving through space, yet also has a frequency to it. And then we get to Fourier series, which is, of course, pertaining to periodic phenomena, where we try to be able to get these periodic functions into a sort of format like this, where we have a constant plus an infinite series, or frankly, n can be decided to be infinite or some smaller, more practical value, where it is a combination of sines and cosines. However, this can be also, with polar coordinates, be simplified further into a form that uses imaginary, or rather complex numbers of the form of constant times e to the 2 pi I times the index here times the time constant. The 2 pi is not necessary, but we have it here with the assumption that the period is 1 unit, and so it works out simply this way. And as you can tell, that this therefore contains a real part to the function, which is by Euler's formula found with cosine equaling. You may be familiar with this formula, and there's also the imaginary part using the sine equivalent. And there's also important to note that with this imaginary form, the index goes from negative n to n as opposed to from 1 to n. And this is important because a real Fourier series has the symmetric property, which is to say that c to the the c sub negative k is equal to its complex conjugate for the positive k. And if you look over back at this formula here, that would essentially cancel out. It's a bit difficult to show in this slideshow, but that does cancel out all the imaginary parts of the um, Fourier series that is created, therefore leaving only real parts, since a real Fourier series. Now I'll briefly mention some applications we encounter with perhaps the most obvious being signal processing, heat distribution, specifically the problem of finding the distribution of heat through a ring with an initial starting temperature throughout it was the impetus for Fourier to come up with the Fourier analysis. However, there's also fluid flow, which comes up a great deal in partial differential equations. In fact, the two fields are intertwined considerably. Some even consider, well, we don't need to get into that. But seismology for trying to understand how waves can combine, and also for understanding building structures and how to avoid buildings collapsing from harmonic oscillations. Spectroscopy for determining the composition of a substance by the energy levels of the elements contained in it. Processing of sensory data, this comes up primarily with visual and auditory information. And I mentioned before also the compression of audio information. This is in fact, some file formats is saving the, I believe, the more complex Fourier form to make it take up less space. And supplemental resources, the Stanford Engineering Everywhere has a specific class, the Fourier transform and its applications, which has a series of 50-minute lecture videos that go through Fourier transforms and also the Fourier series to begin with. I also borrowed a book from the library on linear partial differential equations. Here it is. And highlights of the history of Fourier transforms, where I got that catchy quote in French, as well as a bit of information about the ring and heat distribution being the start for it. In case that's my presentation.